Hi, guys. We'll start in 5 minutes. Can you guys hear me?
Yes, sir.
Okay, great. We'll start in 5 minutes. Yeah.
Okay. Hello. Start பண்ணியோட வால்யூம் 2.2 அவ்வளோதான். 2 + 0.5 இல்லை 2.2 + 0.5.
Yeah. Hello. Can you guys hear me?
Yes, sir.
Okay. Can you guys see the screen also?
Yes, sir, but it is blank right now.
Yeah. So someone asked what is the answer of 10th question of assignment 4. So assignment 4, I'll just yeah. Okay, so the question is f of x equals c into 2x square minus 4x when x is between 1 and 3. Just a second. When x is between 1 and 3 and at 0 otherwise. So we are asked what is the value of c. Wait. So what we do here is basically we integrate f of x dx from minus infinity to infinity since this is a continuous variable. So minus infinity to infinity f of x dx will be equal to 1. Since this is a probability distribution function, right, we can break this up into 3 parts: minus infinity to 1 f of x dx plus 1 to 3 f of x dx plus 3 to plus infinity f of x dx. So this one becomes 0 and this one becomes 0 because the function is 0. So what we are left with is f of x dx in the range 1 to 3 is equal to 1. Okay. So now what we have is f of x is c into 2x square minus 4x dx into 3 equal to 1 is c into x square dx minus 4x dx into 3 equal to 1. This will that implies c into 2x cubed by 3 minus 4x squared by 2. If we put the values into p cube is 27 by 3 minus 2 into 1 cube is 1 by 3 minus 2 into 3 square is 9 minus 2 into 1 square is 1. 8. Mm, mm, mm. 54 minus 2 is 52 by 3 minus 18 minus 2 is 16 into c equal to 1. That implies 52 minus 48 by 3 into c equals 1. So it is take this here. We have 4 by 3 c equals 1. That place c equals 3 by 4 or 0.75. Right. So, but the option is not there. Okay. Okay, so I can see that some of you have also asked this question on the discussion forum. So I think it's best to like wait for a reply on the discussion forum, and probably like most likely in cases like this, they'll give you a grace mark for the answer if yeah it's 0.75. Otherwise, if there's another printing mistake or something, they'll probably give you a grace mark. So I would suggest just wait for a reply on the discussion forum. Right. Yeah, it turns out to be 0.75. Okay. Is that clear? Okay. So, yeah, hi everyone. This is Arpit. I am here. I'm your TA for this course, Introduction to Biostatistics. And today we are at our live session 6, where we'll discuss questions related to whatever was taught in week 6. So related to central limit theorem and confidence intervals. Just a second. Yeah. So yeah, as always, here are some important links. The first is the link to the live session, which you have joined. The second is the link to the YouTube channel where all the recordings of the live sessions are uploaded. So I uploaded the recordings for the last 2 classes also. So week 4 and week 5. This week's I'll upload today after the class. And there's a Google Drive where the materials for the live session are also uploaded. I think I have uploaded all of the things, but if not, I'll check and upload it today. So we'll get started with practice assignment 6. So the first question is, what happens to the variance of a sample if the sample size increases and decreases respectively? Right. So we know that the formula for sample variance is basically population variance divided by root of n. So sample variance is indirectly proportional to root of n. So that means if n increases, this decreases. If n increases, this decreases. And if n decreases, this increases. Right. So the answer should be here option B. If sample size increases, the variance of the sample decreases, and if sample size decreases, the variance of the sample increases. Right. The next question is, suppose the heights of adults in a certain population follow a normal distribution with a mean of 170 centimeter. So we are given that the mean is 170 centimeter, right? And a standard deviation of 8 centimeters. So standard deviation is 8 centimeter. These are all population parameters, right? These are not for a sample. So we have written sigma here and mu here. If a random sample of 64 adults, so n is equal to 64, is selected, what is the probability that the average height of the sample falls between 168 and 172? So what is the probability that the average height, which will be x bar for the sample, falls between 168 and 172? That's what we are asked, right? So probability that the sample mean falls between 168 and 172 will be equal to, so what we'll do here is we'll convert this middle term into a z-score so that we can just look up the standard normal table. So we'll define z equal to x bar minus mu divided by sigma by root n. Right. So here, basically we are using sigma by root n because the variance of the sample is sigma by root n. Right. So this is, we are subtracting the mean and dividing by the variance so that we get a standard normal distribution. So applying that here, what we get is 168 minus mu by sigma by root n less than x bar minus mu by sigma by root n less than 172 minus mu by sigma by root n. So this middle term is nothing but z. I will input all the values that we have. So the mean is 170 and sigma is 8 and n is 64. So 168 minus 170 divided by 8 by root over of 64. Again, 172 minus 170 divided by 8 by root over of 64. So this is 2. Root over of 64 is 8. So 8 divided by 8 is 1. This is minus 2 actually. Yeah. Less than z is less than, again 172 minus 170 is 2. Is again 1. So this is what we need to look up. Now again we can, what do you say? Since the table that we look at will basically tell us like for the z-score. Okay, let me just share the table. Okay, so this is the table that we'll be using. And if you see here, what the table gives us is the probability of a value to be less than equal to a certain value. So probability that z is less than equal to 1 or less than equal to 2, that kinds of things we'll get. So we can't directly get the value of z is greater than -2, right? So what we'll do is we'll try to put our this equation in terms of that. So what we get when we do that is, second, yeah. Yeah. So this is basically that Z lies between -2 and 2. So that basically means that probability that Z is less than 2 minus probability that Z is less than -2. Right. So uh, this we can break it up into two parts like this. And in the table, since we can't look up negative values, what we'll do here is basically we'll use, so we know that probability that Z is less than -2 will be equal to 1 minus probability that Z is less than 2. Right. So since in the standard normal distribution, what we have is something like this. So we have a normal distribution which is centered at 0. Now what we want to find is probability that Z is less than 2, so which is this part. So what I'm saying is this is nothing but, since the distribution is symmetric, this area will be equal to this area, right? And this area is basically 1 minus probability that Z is less than 2. So this whole part is the probability that Z is less than 2. So 1 minus that will give us this area, which is equal to this area, right? So now if we put that into our formula, we get probability that Z is less than 2 minus 1 minus probability that Z is less than 2. So it's probability that Z is less than 2, 2 into this minus 1, right? So this value, so probability that Z is less than 2 is a value that we can directly look up in the table. So how we do that is, again, share the table. Yeah. So we want the probability that Z is less than 2. So for that, what we need to do in this table is basically look up here on the left-hand side column where we find 2.0, right? And since the third, we are trying to look at 2, so the third digit will again be 0. So we'll take the first value here, the first column here. So it's 0.9772, right? So that is the value, that is the probability value of Z being less than equal to 2. So it's 2.00. So it's 2.00. So the first column and this row following 2.0. So it's 0.9772. Now, if we put that value here, what we basically get is 2 into 0.9772 minus 1, which is nothing but 1.9544 minus 1, which is 0.9544 or 95.44%. Right. So the answer here will be option B, 95.44%. Right. So in many cases, you might have, so there are these very standard values of z-score that you will basically come across. So for example, um, things like what is the z-score if the confidence interval is 95% or 99%. So those things, if you just remember a few of those values, it will be faster for you to solve these questions. Otherwise, you will probably get a table during the exams, which you can look up to get at the value, right? So what we did here was we transformed the variable into a z-score and then basically looked up the value in the table and arrived at this answer. Right. It's 95.44%. Question 3. if a sample population of size 38 is selected from a population with mean 70 and standard deviation 5, the standard error of the sampling distribution of the sample means is dash. So what we have here is that we have n, which is equal to 38. We have mu, which is the population mean, which is 70. And we have the population standard deviation, which is 5. Right. So standard error of means, standard error of sampling distribution of sample means is nothing but sigma by root n, which is again nothing but the standard deviation of the sample that we take. So we'll just put the values in this formula. So it's 5 divided by root over of 38. This will be 5 divided by 6.164, which is approximately 0.81. So the answer here will be option C, 0.81. The next question is a test is conducted for H naught or the null hypothesis that mu is equal to 50 with sigma is equal to 5. Sample size of 36 has x bar equal to 52.5. So what we are given is x bar equal to 52.5. We have mu, which is population mean, is 50. We have sigma, which is population standard deviation, which is 5. What we are asked is the test statistic is dash. So dash. So the test statistic is nothing but the z-score, which is x bar minus mu by sigma x, right? And sigma x is nothing but sigma by the root over of n, right? So, okay, sample size is n, which is 36. So this will be 5 divided by root over of 36, which is 5 by 6. So we'll input these values here. So x bar is 52.5 minus 50 divided by 5 by 6 is equal to 2.5 divided by 5 by 6, 25 by 10 into 6 by 5. So 5, 5, 2 and 3. The answer here will be 3. So our answer is option B, 3.0. Okay. The next question is, in a study, the heights of individuals in a large population are normally distributed with a population variance. So this will be sigma square. Population variance of 36. A researcher takes a random sample of 49 individuals from this population. So basically, our sigma square is 36. The sigma will be 6. And we have n equal to 49 from this population and calculates the sample mean and sample variance. So sample mean and sample variance from the sample of 49 individuals. Assuming that the sample provides an unbiased estimate of the population, what is the expected value of the sample variance S square? So when we say that the sample provides an unbiased estimate of the population, what we mean is basically that whatever we estimate from the sample will be representative of what is there in the population, right? So when you say that S square is a unbiased estimator, that means S square will be equal to sigma square, which is the population variance, which is given in the question is 36. So the answer here will be 36. Right. So the expectation of S square will be equal to the variance of the population. question number 6. So if the standard deviation of the population in is 70, so basically sigma is given as 70 and the sample size is 35, so n is equal to 35. Then what is the standard deviation of the sample? Again, so this is a direct formula. Standard deviation of the sample is equal to sigma by root n, which will be equal to 70 divided by root over of 35, which is which is nothing but 70 divided by 5.916, which is approximately 11.832. So the answer here will be option C, 11.832. Is that clear? Okay. So the next question is the lengths of a particular species of fish in a lake follow a normal distribution with a mean of 35 centimeter and a standard deviation of 5 centimeter. So here we are given population characteristics. So mean is 35 and standard deviation is 5. Right. If a random sample of 100 fish is selected, what is the probability that the average length of the sample falls between 34 and 36? So a random sample n is equal to 100. Right. So what is the probability that the average length falls between 34 and 36? So we want to find the probability that x bar lies between 34 and 36. Right. So we'll again transform this into a z-square. So z equal to x bar minus mu by sigma by root n. So probability that 34 minus mu by sigma by root n less than x bar minus mu by sigma by root n is less than 36 minus mu by sigma by root n. So mu is 35, sigma is 5, n is 100. 5 by 100 over plus nz less than 36 minus 35 by 5 by root 100. This will be 1 divided by root 100 is 10. 5 by 10 is half. 1 by 0.5 minus 1 by 0.5. And z is less than 1 divided by again 0.5 equal to minus 2. So again, what we have here is we have to look up on the table and find what is the probability that z line is between minus 2 and 2. So this we can again write it as probability that z is less than 2 minus probability that z is less than -2 is equal to z is less than 2 minus 1 minus probability that z is less than 2 into probability that z is less than 2 minus 1. So probability that z is less than 2 is again using the standard normal table. We can look up the value which we just saw for a question before is 0.9772. So what we have here is 2 into 0.9772 minus 1, which is 1.9544 minus 1, which is 0.9544. So the answer here will be option B, 0.9544. Okay. The next question is, a study is conducted to test the null hypothesis that mu is equal to 100 with a population standard deviation of sigma equal to 5. So we are given that mu is equal to 100 and sigma is equal to 5. Then a sample size of 25, a sample of size 25 is taken. So n is equal to 25. And the sample mean is found to be 105. So the sample mean is found to be 105. What is the standard error of the sampling distribution of the sample mean? Again, we are asked the standard error, and the standard error is nothing but the sample variance, which is sigma by root n, which is equal to 5 divided by root over of 25, which is 5 divided by 5, which is equal to 1. The answer here will be option B, 1.0. Right. The next question is, a researcher is conducting a study on the average height of a certain population. The population variance is known to be sigma square equal to 25. So we have sigma square equal to 25. To achieve a 95% confidence interval with a margin of error of 0.5 centimeter for the sample mean, what should be the minimum sample size? So what we are given here is our margin of error, which is E is nothing but 0.5. And our confidence interval or alpha value is 95%. Right. So for the alpha value of alpha of 95%, the z-score, corresponding z-score will be equal to 1.96. Right. So this is because if you have a distribution, a standard normal distribution, so with a mean of 0, so between minus 1.96 standard deviation and 1.96 standard deviation, you have 95% of the data. Right. So the alpha value, this 95% lies between minus 1.96 to 1.96. So the critical z value for this confidence interval is 1.96. So as I was saying before, this is one of the cases in which it would be easier for you to just remember this value. So for 95% alpha value, you should have a critical z-score of 1.96, right? For a two-tailed test. So here we don't care about one side. Here we basically care about both the sides. So basically what you should have here is if you have a distribution like this, So this area should be 2.5%, and this area should be 2.5%. And thus the area in between these will be 95%. 1 minus 2.5 plus 2.5, which is 95%, right? So another way to basically get this Z value from the confidence interval is to look at the standard normal table again. So, but in a reverse direction. So we'll also just do that. So you know how to do that and how to find those values. So yeah. So what we are looking for here is 95% confidence value. But what we want is basically, so the area in the white here, the area shaded in the red, should be 97.5%. And thus the area in the white part, which is to the right, will be 2.5%, right? So as I said before, we need to find a value where basically the right extreme, the area after the right extreme is 2.5%, and the area after the left extreme is 2.5%, right? So in the table, what we need to look for is the probability value of 97.5%, right? So 0.975. So in all of these values, wherever you find 0.975, that should be our value of critical value of Z-score. So if you go to the table and look at it, you'll see that 0.975 we get only here, which is 1.9 and 0.06. So it's 1.9 plus 0.06, which is 1.96. Right. So similarly, if you were to find a point at like 99% confidence interval, so what that means is that 1% which is left out. So basically, the middle portion of the graph should have 99% of the data points. The extreme left will have 0.5% of the data points. Extreme right will have 0.5% of the data points, right? So what you need to look for in this table is basically find the value of basically if the white side on the right hand side, the extreme part is uh, 0.5%, then this part will be 99.5% or 0.995. So we'll look for values which have 0.995. So actually, this is the closest we can get, which is 0.9951. So if we look up for this particular value, the row and the column, it is 2.5 and it is 0.08. So if we add those two, we get 2.58, right? So if the confidence interval is 99%, then our critical Z-score will be 2.58. If the confidence interval is 95%, our critical Z-score will be 1.96, right? So similarly, you can look up for like other values for which you might not know the critical values. You can look it up similarly in the table. Okay. So yeah, in this case, we are looking at 95% confidence interval. So our critical Z value will be 1.96. So what we are asked is what should be the minimum sample size. So what we are asked is N is equal to what? Right. So we know that the margin of error E is given as Z alpha by 2 into sigma by root n. Right. So this is the formula for the margin of error. We are given that E is 0.5. Actually, we can just change the formula to bring the N to the left-hand side and take the E to the right-hand side. So what we can write is root N equal to Z. I'm just writing Z here for short by E. And that implies N is equal to Z into sigma by E whole square. Right. So this will be equal to Z is 1.96 into sigma square is 25. That means sigma is equal to 5. 1.96 into 5 divided by E here is 0.5 whole square. Right. So this is this. Right. So what this will be is, so this 5 will cancel out and we have 0.1 here. So it's 1 by 10. So it's 19.6 whole square, which will be approximately 384 point something, 84.16. So the minimum n value for us, for which we can have a 95% confidence interval with a margin of error of 0.5 will be 384.16. But since n cannot be a fraction, because n is number of samples we are taking, it would be an integer. Therefore, we'll round it up to the nearest integer, which is 385, nearest, like, next integer, basically. The answer here will be 385. Okay. But in the option, if sometimes 384 is given and none of the other options are close by, then you should also select 384. Like, you can also select 384. Okay. Yeah. So next question is, two types of cell lines, cell line A and cell line B, are studied to compare their migration rates. So migration rate is like how fast these cells are moving in a medium, right? Cell line A shows an average migration distance of 120 micrometer, while cell line B shows an average migration distance of 100 micrometer. In a study, 40 samples from each cell line were tested, and the variances of the migration distances for each cell line A and cell line B were found to be 200 and 220 respectively. By using 99% confidence interval, which of the following statements is correct? Right. So the statements are cell line A has significantly higher migration rate than B. B has significantly higher migration rate than A. Result is inconclusive. Both have the same migration rate. Right. So what we need to do here is we basically need to calculate what is the 99% confidence interval for the difference between the means. Right. So what we are given here is basically x bar A, x bar B, 120 and 100. So this is 120, this is 100. We are also given S square, so which is basically the sample variance. This is 200 and 220. Right. We are given a confidence value or alpha value of 99%. And we are given that 40 samples. So n is equal to 40. Right. So as I said before, for 99% significance level or alpha value, the z of alpha by 2 will be equal to 2.58. Right. So again, like, it's easier if you just remember these few values. For 95%, for 99%, it's 1.96 and 2.58. Right. So to calculate the 99% confidence interval for this data, the formula, like, since we are making this comparison, the formula will be x a bar minus x b bar So this is a difference of means plus minus the z-score into SA square by NA plus SB square by NB root over. Right. So once we input the values, we have 120 minus 100 plus minus 2.58 into 200. So our NA is equal to NB is equal to 40 because from each of these population, 40 samples from each cell line were tested, right? This is 200 by 40 plus 220 by 40 put over. So this will be 5 and this will be 11 by 2, which is 5.5. This 120 minus 100 is 20 plus minus 2.58 into 5 plus 5.5, which is 10.5 root over of 10.5. So this will be equal to root over of 10.5 is 3.24 into 2.58 plus minus 20. So again equal to 2.58 into 3.24, which is 20 plus minus 8.36. So this gives us the range, which is 20 minus 8.36, which is 11.64 to 28.36. Right. So the difference between the means of A, cell line A and cell line B lie between with a 99% confidence lie between 11.6 to 28.36. Right. So that means the difference between cell line, so the mean of cell line A minus the mean of cell line B is always positive. Right. So this indicates that mu A minus mu B is greater than 0 always. Right. Or actually the x bar A minus x bar B is greater than 0 always. Right. So what this means is basically that with 99% confidence, we can say that cell line A has a higher migration rate because the mean of cell line A is always greater than the mean of cell line B at a significance level of 99%. Right. Like it falls in the range. Now, if you have questions like this, what you should do is basically use this formula and calculate a range. So if that range is always falls on the higher side always, that means the uh, sorry, that means the first category or the first population, that is XA here that you took, is always greater than the mean of XA is always greater than the mean of XB. However, if you get a range which is always negative, so for example, in this case, hypothetically, let's say our range was from -4 to -2, right? So in this case, cell B, so x bar B minus x bar A would be greater than 0, right? So that means B has higher migration rate, right? And if our range basically includes 0, so for example, you have a range like -2 to 4 or something. So our range includes 0. That means we cannot uh, say that one of them is higher or lower than the other because the difference might turn out to be 0 also or somewhere very close to 0. So not very significantly different. Right? Not significantly different. But for our case, since all of this is positive, we have this, and therefore cell line A has higher migration rate than cell line B. Is this clear? Mhm. Okay. So the next question is, according to the central limit theorem, the sampling distribution of the sample mean approaches a normal distribution as A, sample size decreases, B, population variance increases, C, sample size increases, or D, population mean increases. So the answer is quite straightforward. It's in the definition of the central limit theorem that as the sample size increases, the sampling distribution of the mean approaches a normal distribution. Right. So that basically is the statement of the central limit theorem. Irrespective of what kind of distribution is followed uh, by the uh, population. Right. The sampling distribution of the means will follow a normal distribution if you have enough sample size. Right. So in general, like this is true for what do you say, for symmetric distributions like uh, uniform or binomial distributions, binomial or normal distributions, you will basically have a normal distribution of the sampling distribution of sample means uh, for even low values of sample size, so low values of n. But for other distributions, it's recommended that the value of n is at least greater than equal to 30, right? So if you have bigger or higher values, then the approximation is more normal. Right. The standard error of the mean is given by, so this we know, standard error of mean is given by sigma by root n, which is nothing but here sigma by n raised to power 0.5. Right. Next question is, a population has mean of 50 and standard deviation of 12. So we have mean of 50, standard deviation of 12. For a sample size of 36, so n is 36, what is the standard error of the mean? So standard error of the mean, as I said before, is nothing but sigma by root 10, which is 12 divided by root over of 36, which is 12 by 6, which is 2. The answer here will be option A, which is 2. Right. A 95% confidence interval corresponds approximately to which critical z-value for a two-tailed test? So the answer here is straightforward. It's 1.96. I'll again reiterate how to basically get this from a table so that if you get random numbers here, for example, 90% confidence interval or 85% confidence interval, how to get a z value from it. So here basically, we'll assume that it's a normal distribution. Sorry for the bad drawing. Yeah. So what we want is basically, we want a 95% confidence interval. So that means the data here in between, in this area, 95% of the data should lie. So 5% of the data is outside. And since this is symmetric and we are looking at a two-tailed value, right? So this area will be 2.5% and this area will be 2.5%, right? And when we are looking at our table, what value our table basically gives us is basically what is the So for a given x, this is the value that the table will give you, right? So to get this exact z value or this x value here, we need to make sure that this area that we are getting is 97.5%. So it's 95% plus 2.5%. So 97.5%. And the rest 2.5% is here. Right. So what we need to do is in the table. So we have a table like this. And here all the different probability values are given. So we need to find in the table where is the probability value of 0.9750 or 97.5%. And for that particular value, we need to look at the row and we need to look at the column. So the row gives us the first two digits and the column gives us the third digit of the value. So if you go to the table and find this value, you will see that here you will have 1.9 and here you will have 0.06. So the answer, so the critical z value, the critical, just a second. So the critical z value here will be 1.96. 1.9 plus 0.06, which is 1.96. Right. So I'll just show it on the table again. 0.9750. That's the value we are looking for. So if we look at the table, 0.9750 is somewhere here. We see that the row is 1.9 and the column is 0.06. So it's 1.96. Okay. If the sample mean is 80 and the population standard deviation is 10. So the sample mean so the sample mean is 80 and the population standard deviation sigma is equal to 10. Right. And the sample size n is equal to 25. What is the 95% confidence interval for the population mean? So 95% CI. It's what we are asked. So how to proceed? Basically, this will be equal to x bar plus minus z into sigma by root n. Right. Since we are talking about a single sample and our alpha value is 95%. Right. So z value here will be 1.96. We just learned how to get that from the table. Basically, x bar is 80, sigma is 10, and n is 25. If we put all of these values in the formula, we have 80 plus minus 1.96 into 10 divided by root over of 25. This is 80 plus minus 1.96 into 10 divided by 5, which is 2. It's 80 plus minus 3.92. Right. So 3.92 right. So the answer here is option A, 76.08 to 83.92. Yeah. So with 95% confidence, we can say that the population mean lies between this. Or in other words, if you basically take out more and more samples, 1 out of every 20 times our sample will fall outside the range of the, so our range will fall outside the population mean. So what I mean by that is, for example, let's say this value here is the population mean, mu, right? So our range here is, we are not given the population mean anywhere here, right? So we don't know what the population mean is. But what we got, the value is, the range that we got is, let's say 76 point something to 83 point something, right? So what this means is, if we were going to repeat this, if you are going to take another sample and again calculate the range might turn out to be slightly different, right? Each of the times, some of the times it will be here, some of the times it will be there, right? But once in every 20 times, almost approximately, we'll have a range which falls outside of the population mean, right? So that is what basically it means. Once every 20 times, we might have a range that falls outside the population mean. Right. So this is what basically 95% confidence interval means when we are talking like this. And this is how we calculate basically. So the CI 95% confidence interval is mean plus minus the critical Z value into sigma by root n. So for 95%, the critical Z value is 1.96. Okay. So which of the following statements about confidence intervals is true? So a wider interval means greater precision. A narrower interval means greater precision. Confidence level and confidence interval width are unrelated. Increasing sample size increases the width of the interval. Right. So this is the formula for the confidence interval. So basically our confidence interval is x bar plus minus z into sigma by root n. Right. So if you increase the sample size, basically, so this ranges from x bar minus z into sigma by root n to x bar plus z into sigma by root n. Right. So if you increase the value of n, uh, this value becomes smaller. This value becomes smaller. So the range that you have, or the width of the interval, basically uh, decreases when you increase the sample size. Another way to look at it is like the width of interval will be equal to this minus this. So which will be equal to 2 into z sigma by root n. Right. So as you increase the sample size, the width of the interval decreases. So this option is incorrect. So again, confidence level and confidence interval width are related. They're not unrelated. So this is false. This is because so the confidence level, for example, let's say we talk about 95% confidence interval here. So the Z value will change accordingly, and the Z value also affects the interval width, right? So they are related. So if you have a 95% confidence interval, you will have a, if you're looking at a 95% confidence interval, the width that you get will be different than the width that you get for a 99% confidence interval because they are related and the Z value changes according to the confidence level, right? Or the percentage that you put here. So this is incorrect. A narrower interval means greater precision. That is true. A wider interval means greater precision. That is false. So this is because, so for example, you're trying to estimate the population mean, which is somewhat like this. And let's say you have a interval which is like this, and you have another interval which is like this, right? So what this interval tells you is that the population mean falls within this range, which is a small range. But what this interval tells you is that the population mean falls within a wider range of values. So the population mean can be anywhere from here to here if you don't know what the population mean is and you're just trying to estimate it from the sample. So this gives you less precision or accuracy, and this gives you high precision, since you can narrow down the position of the mean, right? So the answer here will be option B. A narrower interval means greater precision. For a 99% confidence interval, the margin of error compared to a 95% interval is larger, smaller, the same, or zero. Right. So when we are looking at a 99% confidence interval, so let's say this is a 95% confidence interval, and this is our population mean, then basically our margin of error is basically this length, right? So this is how much error uh, we can have when we are trying to estimate the mean. Now, if we have a 99% confidence interval, we'll have a larger width in general. Now, why is that? Because if you look at the formula for the width of interval, width of interval is equal to 2 into C into sigma by root 10. So this Z here changes based on 99% or 95%, right? For 95%, just a second. For a 95% confidence interval, we have a Z of 1.96. For a 99% confidence interval, we have a Z of 2.58. Right, so the Z value increases, so the width of the interval increases as we increase the confidence level. So that's why the margin of error becomes larger, which is option A. Another way to think about it is that, so if you want to say with a higher level of confidence that your mean lies within a certain range, then the range that you will take will be larger than the range that you take if you are okay with being less certain, right? So what this basically means is that in this 95% case, we can tolerate 5% mistake. So once every 20 times if we take samples and the range falls outside the mean, that is okay, right? That is bearable for us once every 20 times. Approx. Right. But in this case, we have a stricter confidence level. So what we are saying is once every 100 times, we can tolerate a mistake like this. So when the range falls outside the population mean. Right. So yeah, to have that more overlap with the population mean, the range or the width of the interval is larger for 99% and smaller for 95%. Okay, is that clear? Okay. So the next question is, if the population distribution is highly skewed, the center limit theorem tells us that the sampling distribution of the mean will still be approximately normal when the sample size is very small, the sample size is large enough, the population mean is zero, the population variance is small, right? So the answer here will be option B when the sample size is large enough, because that is what the center limit theorem tells us. But if you basically were trying to reason it out and think about why this is happening. So for example, let's say you have a highly skewed distribution like this, right? And let's say you basically, what do you say? It doesn't matter what the population mean is. The population mean can be 0 or greater than 0 or 100 or less than 0, -1, -10, whatever. That does not affect basically, what do you say, how the sampling distribution of the mean will change, right? But if you have a small sample size in this case, like let's say we are picking only 3 samples, and by mistake, not by mistake, and randomly, we basically pick these 3 points, right? So the mean that you will get for the population will be somewhere here. Now again, you say let's say you take 3 points and you get 3 points which are here. So the mean that you get in that case will be somewhere here, right? Sampling distribution of the mean. Yeah, so basically the values of mean that you will get for small points will be highly variable. So the mean values that you get from each of these samples might vary a lot. But if you are taking a very large number of random samples, so let's say you're taking 20 or 30 points, you might have some points which are clustered over here, some points which are clustered over here, and some points which are basically somewhere here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Right. So you get all these different points and you then take the mean of it. So that will give you a more stable approximation of the mean, and it will be closer to the mean of the actual distribution. Right. So if the sample size that you are choosing is large enough, in that case, you will basically get approximately normal distribution of the sampling means. Right. And yeah. The next question is, a researcher wants a 95% confidence interval for a population mean with a margin of error of 1 unit. The population standard deviation is known to be 5. What is the sample size that is required? So the population standard deviation sigma is given as 5. So sigma is given as 5. Alpha is the confidence level, which is 95%. Margin of error is 1. So E is equal to 1. Right. What is the sample size that you need? So we know that E is equal to Z into sigma by root n. That means the root n is equal to Z into sigma by E, and n is equal to Z into sigma by E whole square. Right. So we are for a significance level of 95%. We have the corresponding Z value, which is 1.96. So we'll input all these values that we have. 1.96 into 5 divided by 1 whole square. Okay, 9.48, 34, 9.8. This is 9.80 whole square, which will be somewhere around 96.04. Right. So we should have at least 96.04 samples so that we get a 95% confidence interval. So from the options, we see that the closest value, which is higher than 96.04, is 97. So the answer here will be 97. So this can be approximated to 97. Right. In general, these questions will have what is the minimum sample size that is required. Right. So the minimum sample size is 96.04, which can be approximated to 97. Or if you don't have 97, if you have 96, you can also approximate it to 96. Okay. The central limit theorem is most useful because it allows us to use normal approximation for sample proportions and means, reduce the population variance, eliminate sampling error, and guarantee the sampling mean equals to the population mean. Okay, so you cannot make the guarantee. So this is a false statement. Right, like you can make a guarantee as such, like you can tell with like some level of confidence, but you can't get the exact value of the population mean. You can tell a range within which that value lies, right? Then eliminate sampling errors. So sampling error is uh, sampling error reduces as you increase the sample size according to the central limit theorem, but it does not eliminate sample error, sampling error, right? There'll always be error, and that error can be eliminated by using other methods of sampling or uh, what do you say, by sampling better. For example, if you have a structure in your population, then you should have a stratified kind of sampling and follow better sampling protocols that can reduce your sampling error, right? Reduce the population variance. So the central limit theorem does not talk about reducing the sampling and population variance that much, but what basically it allows us to do and what basically gives us the most power is that we can use the central limit theorem to do option A, which is use normal approximation for sample proportions and means. So we can basically, what do you say, from a sample, we can approximate what will be the values in the population for the means or the variance or other things. And how, and we say basically, as we increase the sample size, the distribution of these sample proportions and sample means that we get are normally distributed. So it's easier for us to make those calculations and basically uh, compare those using like standard normal curves and z-scores and confidence intervals as we have been doing over the course of this week. Right. So yeah, so that was I think all the questions for this week. Does anyone have any questions or doubts? So I'll be around for another 10-15 minutes. If you guys have any other questions or doubts, feel free to ask. If you want me to repeat any other question. So as I said before, like for the assignment 4 question number 10, many of you have asked on the discussion forum regarding that, and it's better for you to basically wait for uh, a reply there. Right? So there are like other TAs and sir who basically manage the course and grade your assignments and all. So I'm not involved in grading your assignments or conducting the exam or anything. So it's better for you to basically wait for them to take some action or basically reply on the discussion forum. But yeah, it seems like the answer is that the options that are provided are probably misprinted. Even like in the in the assignment solution, I think the last step is probably misprinted. Yeah. Anyways, like it's better for you guys to wait for sir or someone on the group to basically reply to your messages on the discussion forum. Yeah. Apart from that, yeah. So if anyone has any questions or doubts apart from that, we can discuss that. I'll be around till 7:45. So just feel free to like write on the chat or unmute yourself whenever you feel like asking a doubt. Yeah. Okay. So we'll stop here for today, and we'll continue in the next week. Thanks for attending. Next week, as in the next class, is this Friday for week 7 lecture. So yeah. So I'll see you guys tomorrow. Uh, Not tomorrow, this week, Friday. And yeah, I think that's it. Bye. And yeah, we'll meet again. Bye.